Bismillah ar-Rahman ar-Rahim, and welcome to lecture number 21 for basic engineering mechanics. In this lecture we will continue our discussion for equilibrium of a rigid body in two dimensions, and then we would look at some special cases for equilibrium in two dimensions, which is 2 and 3 force members, and then today we will start our discussion of equilibrium in 3 dimensions, and we'll see what type of support reactions can we have for 3 dimensions. Okay, so let's start with another example. So here again we want to determine the support reactions on the member in figure 5-19a. The collar at A is fixed to the member and can slide vertically along the vertical shaft. So here we have this member which is shown in blue, which has one force acting on it, which is 900 newtons, and it also has a couple moment acting on it, which is 500 newton meters, and it is supported at both ends. One of the ends is supported with this roller at B, and the other support is with this fixed support at A. So this support, as the statement says, that it is allowed to slide up and down, but it cannot rotate and it cannot slide, it cannot move horizontally. So the first thing again that we always have to do is to draw a free body diagram, and so I'll just draw first of all we draw a sketch of our first we draw this, then we draw the second part like this, so we have drawn the outline of our member. And so let's now draw the active forces. So we have a 900 newton force acting here, which is acting downwards, so 900 newtons, and then we have a moment which is 500 newton meter. Okay. So now we are done drawing the active forces and couple moments. So now we should draw the reactive forces. So this roller would provide a force which is vertical to the surface of the roller. So that means that we would get something like a force. So I'll draw my reactive forces with a darker color. So we would have a reactive force here, and I can call it FB, and then this support here would provide a horizontal force. I can call it FAX, and it would also provide a couple moment, which I can call as MA. And as we saw earlier, that to complete our drawing free body diagram, we need to draw an axis. So this is our x-axis and this is our y-axis, and again we also need to show all the dimensions which we would need for our analysis. So this is 1.5 meters, and this again is 1.5 meters to this point, and this angle is 45 degrees, and this distance is 1 meters. So this completes our free body diagram. Free body diagram. The next step again is to write the equations of equilibrium. So we have the first equation, which is sum of all the moments in x is equal to 0, and the only force, sum of all the forces in x are equal to 0. The only force in the x direction is this Fax, which simply means that Fax has to be equal to 0. The second equation again is to say that sum of all the forces in y are equal to 0, which basically means that Fb minus 900 equals 0, which means that Fb is just equal to 900 Newton. Okay, so the third equation is equation for the moment, and I can choose any point to write the equations of the moment. And as we saw earlier, that we choose a point which is most where calculating the moment is the easiest, so we just choose a point A. We choose the point A, and this becomes so we have this 900, so we have a moment MA, sum of all the moments at A. So this is different from this MA. MA plus 500, which is the couple moment here, and then we have a couple moment because of this 900 force, which would be equal to plus this would produce a counterclockwise moment. Clockwise moment we represent with a negative sign times 1.5, and this last term would produce a moment which is counterclockwise, and again because Fb is again 900, so I can just say 900 times, and the distance is 3 meters till this point, and then 1 divided times sine of cos of 45 for this distance, so we get 3 plus 1 divided by square root of 2. And now we can solve this equation for MA. Once we solve for MA, we get MA is equal to 1486 Newton meter. Okay, so I'm not going to go over every step of this calculation, but I think it should be clear enough that we can solve this equation pretty straightforwardly, and this comes out to be negative actually, which basically means that the moment couple moment has to be in the counterclockwise direction. This moment we defined in clockwise direction, so I think we should have a negative sign here, and then this would come out to be positive, which means that the moment actually this again so I guess I have, so this again has to be negative, and the result turns out to be equal to positive number here. So that means that moment is actually in the direction as shown here. So now we look at some special cases for rigid body equilibrium, and one of the special cases is what we call a two force member. A two force member is any member of our object which only has two forces acting on it. So like in this case we have this member AB, and there are only two forces, one force acting at A and the other force acting at B. It does not have any other force acting on it, and it does not have any other couple moments acting on it. So that is why they are called two force members. So given that we only have two forces and we still want to use the same equations as we previously had, so we need that sum of all the forces should be equal to 0, and because we only have two forces, that means that F1 should be equal to minus F2. So if the two forces is F1 and F2 like shown here, then both the forces should be equal and opposite in direction, as this statement is telling us here. So these two forces need to be equal to each other and they have to be opposite in the opposite direction. So that is the first thing that we learn from two force members, that the two forces need to be equal and opposite in direction. And the second thing, these two force members also have to satisfy that sum of all the moments have to be equal to 0. And because we already know that the two forces are equal and opposite in direction, that implies that the perpendicular distance between these two forces has to be equal to 0. Like in this second case, if the perpendicular distance is not equal to 0 as shown in the second diagram, then we would have a couple moment formed because of these two forces, which then the couple moment will not be equal to, the sum of all the moments will not be equal to 0. To satisfy both the conditions, we need the forces to be equal and opposite in direction, and we need the forces to be in a same line. Okay, so both these first and second cases are not allowed. The first case is not allowed because these two forces are not equal, their directions is not opposite to each other, and the second case is also not allowed because these two forces do not lie along a same line, which means that the couple moment won't be equal to 0. So these two bodies cannot be in equilibrium. And so the only way a two force member can be in equilibrium is when the two forces are opposite and both the forces are acting along the same line. So the only allowed case is this third case. So just to sum it up, if we have a two force member, the two forces need to be equal and opposite in direction, and the two forces have to lie along the same line. Okay, so the next case, special case, is the case of a three force member. And for a three force member, again we need that the sum of all the forces need to be equal to 0 and sum of all the moments have to be equal to 0. The first condition is trivial. Sum of all the forces can always, we can choose the three forces such that their sum is equal to 0. That is not very difficult. So the first condition, sum of all the forces equals to 0, does not help us at all, because we can say that F1 plus F2 plus F3 is equal to 0 does not help us in determining any single forces or put any conditions on these forces. But the second moment, sum of all the moments equal to 0, does put some conditions on the forces, that the type of forces that we can have. And let's see. So we can have one of two options for three force members. First option is that all of these three forces should be concurrent. They should be passing through the same point. So then if we were to find the moment at point O, then the moment would be equal to 0 at this point, because all the three forces are passing through this point, and so the perpendicular distance for all these three forces would be equal to 0. And the second case would be when all the forces are parallel. So if all the forces are parallel, then we can choose these forces in a way that we can still get equilibrium. But what we cannot have is that if two forces are not parallel, so maybe we have this force F1 acting on this body and this force F2, and this F3 maybe is acting in this direction, okay. And so as we can already see that these three forces are not concurrent, and so if we were to draw a line along here and a line along here, these two forces pass through this point here, and if we were to, let's just call this point A, if we were to sum all the moments at A, this will not be equal to 0, because these two forces F1 and F2 will not produce any moment at point A, and the only moment would be equal to F3 times the perpendicular distance, which will not be equal to 0. So if two forces are not parallel, that means they in a coplanar system, anytime we have two forces which are not parallel, they would be intersecting at any point, and to make sure that the moment is 0 at that point, the third force should also be passing through that point. So that is why we can either have concurrency, that all the three forces are the line of action of all the three forces, it meets at some particular point, or we can have that all the three forces are parallel, in which case we do not have a point of concurrency even for two forces. So the moments of these two forces can cancel out at this point, and the moments of these two forces can cancel at this point. So I hope the reasoning is clear, that for three force members in coplanar system, we need to have either one of these two conditions. Either all the three forces should be parallel, or they should be concurrent. So let's move on, and now we look at one example how we can use the concept of two force and three force members to simplify our calculation. So here we have a lever ABC. So this is the lever which with a dark blue color ABC, and which there is a pin supported at A. We have a pin support at A, and we have connected a short link BD. We have a short link BD, and the other side is also a pin support. If the weight of the members is negligible, determine the force on the pin on the lever at A. We want to find the force provided by the pin to the lever at this point A, which is the reaction force. So how does two force member concept help us here? In this case, we can see that this member ADB, member DB is a two force member. What does that mean? Well, that means that the force on B and D, they would be equal and opposite and along the line of action. So the forces, the only force that can be at point B is going to be in the direction like this, and same as the D, the only force at D has to be in the direction of the line from B to D. So that means if we were to draw the free body diagram of our original lever, so I'm going to draw the lever first. So this is our lever. We have a 400 Newton force acting towards the right, and then this at this point B we would have a force which would be at 45 degrees, because this is point 2, this is also point 2, so this angle needs to be 45 degrees, and this is the first force support, so I'll just call it FB, and this point A, the support provided by point A would be in terms of two forces rather than one. So we get Fa x and Fa y. Okay, so now we have three unknowns, and we can write three equations. We have the sum of all the forces in x have to be equal to 0, sum of all the forces in y have to be equal to 0, and sum of all the moments at any point. So let's just choose the point A has to be equal to 0. So we can just use the concept studied before to solve for these three unknowns using these three equations. And notice, if we were not to use the condition for this two force member, we would need to replace this B, support B, with two forces rather than one, and then we would need to solve for this separately to get more equations. But knowing that this is a two force member, we can directly say that the force has to be along the direction of BD. So I'm not going to go through all the mathematics. I trust that you guys at this point are comfortable enough in the mathematics. Okay, so so now we look at some support reactions for 3 dimensions. Okay, so as we discussed earlier, our next topic is equilibrium in 3 dimensions. And so first of all, we need to look at the different types of supports we can have in 3 dimensions. So these 3 supports are pretty similar to what we used to have in 2 dimensions. If we have a cable support, this cable would provide a force which is along the direction of the cable, and we'll get one unknown. This is exactly what we had before. And if we have a smooth surface support, this surface would provide a support which is perpendicular to the surface. So we have a force here. If we have a roller, that is exactly similar to the smooth surface support, and we get a force which is perpendicular to the surface. So if we have a ball socket is something which allows rotation in all the 3 directions, but it does not allow translation of this point in any of the 3 directions. So because the translation is restricted in all the x and y and z directions, so we would have to replace this point with x, y, z 3 forces. And the second case, the fifth case, is that of a single journal bearing. A journal bearing is something which allows rotation. So journal bearing would allow rotation in this direction, and it would also allow translation along this direction. What is not allowed is that it will not allow, I can show that with red. So rotation is not allowed along the z-axis, and it's not allowed along the x-axis, and translation along the y and the z-axis is not allowed. So for every restricted motion, we would have a support reaction. So we would have 2 forces, Fx and Fz, to stop the translation, and we would have 2 couple moments, one in Mx and one in Mz, to stop the rotation in these 2 axes. Okay, so the second case is single journal bearing with square shaft. A square shaft is different from a regular round shaft, that a square shaft cannot rotate. So now even the rotation along this axis is not allowed. That means we also get a support couple moment along the y axis. A thrust bearing is something which stops to and fro motion. It also provides a thrust. So now we would replace this thrust bearing with 2 moments and 3 forces as shown in this diagram. A single smooth pin is exactly what we used to have before, but now this smooth pin only allows rotation in one direction, and translation is restricted in all the three directions, and rotation is restricted in the other two directions. So we would get 5 unknown support reactions as shown here. Now, a single hinge is something which again allows only rotation along one direction, and this is what the support reactions of a single hinge are exactly the same as that of a smooth pin. And a fixed support does not allow rotation and does not allow translation. So the support reactions for a fixed support in 3 dimensions would be given by 3 forces and 3 coupled moments as shown here. So I hope this is clear. This is it for this lecture, and in the next lecture we will look at how do we solve problems for rigid body equilibrium in 3 dimensions. So assalamu alaikum warahmatullahi wabarakatuh.